Okay. Okay, let's start. Welcome to our final seminar of the fall semester. We kept the best for the last. We're very pleased to have Professor Laura Albert with us today. She is a professor and David Gustafson Department Chair of Industrial Systems Engineering at the University of Wisconsin-Madison. Her research interest is in operations research, with a particular focus on discrete optimization with applications to homeland security and emergency response problems. She has authored more than 70 publications, and she has a long list. I would say that she is a member of the American Association of Advancement of Sciences, and she received the Fellow Award, Institute for Industrial Engineers Fellow Award, the Informs Impact Prize, the NSF Career Award, a Fulbright Award, the Department of Army Young Investigator Award. Her research has been supported by National Science Foundation, the Department of Homeland Security, the Department of the Army, and the Sandia National Laboratory. She's also the current president-elect of the Informs. And the best part, and I advise all of you students to go read it, right? She has a blog called Punk Rock OR, and it's really punk. And I actually read some of those, and they're amazing stories. I really encourage you to go read it. So without further ado, let's, sorry?
Definitely a top OR blog.
Yes, and coming from another top OR blogger.
less prolific.
Yeah, that's true. Yes. So welcome, Professor Albert, and we look forward to hearing from you.
Well, thank you. Well, thank you for that warm introduction, and it's great to see all you here. This is wonderful. I've lived in Wisconsin for 10 years at this point, so when I got invited, I said, give me the date in December, I'll come. It was snowing, it was 8 degrees when I arrived this morning, and I'm really happy to be here. I really am happy to be here. They're recording this talk. I should have deleted the slide because it shows Goldie the Gopher in a positive light, but it's good to be here. I'm going to talk about some of my recent research in election resilience today, but first I'm going to put my department chair hat on and just tell you about a few things, just a couple things about my amazing department. This is a picture of all of us. We have about 20 faculty members and 6 teaching faculty and instructional staff. We had a couple of new additions to our department, 2 assistant professors this past year. Professor Tony McDonald comes to us from Texas A&M. He's an expert in human factors and also machine learning. And he studies things like distracted driving, drowsy driving, transportation, and also nursing. And Professor Hentang Quinn is also an assistant professor. He comes to us from Iowa State, and he's in the manufacturing area. And most of our manufacturing is on the soft side. He actually does like real manufacturing with equipment. He does additive manufacturing, focusing on manufacturing in outer space. So he works closely with NASA, among others. And we are delighted that they've joined us. And I love bragging about my faculty members. So you're going to have to indulge me for a minute, but we have 3 faculty members with major awards in the last year or so. Associate Professor Kaibo Liu won the ISyE Award for Technical Innovation in Industrial Engineering. Professor Oz Alagaz, he's a full professor, was inducted as an ISyE Fellow. And then very recently, Professor Rob Radwin received an award from ISyE with a really long name, the Boeing Award for Excellence for Collaboration in Productivity, Workplace, Safety, and Ergonomics. So these are just a few of the things that our faculty have been up to recently. All right, so moving on to my talk. I've studied critical infrastructure protection and discrete optimization. That's like my bread and butter, like how to manage risk in public sector systems. And during the pandemic, it was July 2020, I barely left the house, right? And I ran into a political science professor, and we were socially distancing outside. And he said, Laura, queuing theory and location analysis is so important for elections. And it was like catnip to me. And I was so curious and interested. And so we started talking and sharing notes. And at the time, this was like right between all the spring primaries and the general election. And the spring primaries did not go smoothly in 2020, especially in Wisconsin. We had our spring primary the first week in April, and this was the first set of primaries during stay-at-home orders that most states had. And it was really hard to hold primaries. You rely on volunteers and poll workers. The median age of a poll worker in Wisconsin is over the age of 60. So you can imagine that we were lacking in volunteers and poll workers. And the city of Milwaukee combined its 182 polling locations down to 5 big high school gymnasium polling centers. And it did not go well. There were really long queues. It made national news and not in a good way. And so we were just interested in what we could do to help. And what was really interesting is that election officials were willing to try new things. So they were interested in design questions, as well as like operational resource allocation applications. I was familiar with a lot of the OR work in the literature and was really interested in this new vulnerability that really emerged during COVID-19. That wasn't the only disaster that affected recent elections. Hurricane Sandy struck a week before the 2012 presidential election. So we were like 2 of the last 3 presidential elections were affected by a disaster. So there's all sorts of emergencies and disasters that occur for elections, and election officials have to be prepared for all of that. But COVID-19 was an opportunity for us to plan for a more resilient future. And a lot of the decisions they have to do with resource allocation, planning under uncertainty, discrete decision-making, things that we do really well in operations research. Also, equity is a big concern because some communities are affected by these decisions more than others. So we got to work at this time. Basically, the work was done by my PhD student, Adam Schmidt, who had a lot of courage to just tackle some of these problems. And we worked really hard in the summer of 2020 on our first paper, and we worked on a couple other problems since then. So my talk is going to have 4 parts, and it's going to overview 3 papers. So I won't get super in depth, and I'll throw some math in there occasionally. Some of the math is an intentionally small font, so you don't read too much of it. You can read the papers, but I want to explain some of the insights and the findings. Our first paper that a draft of it was finished in September 2020. And then we shared with election officials, really focused on in-person voting at scale in a presidential election. And after we finished that paper, we were interested in some other questions that maybe weren't being asked from a scientific point of view. One is, how would you consolidate polling locations? We thought this was going to be like a really easy problem, like the assignment problem that you introduce and solve optimally in an intro class. And it turns out it's pretty rich and interesting. And then we're also interested in locating dropboxes. Wisconsin used dropboxes in 2020, and we were interested in like how to use analytical methods to make good choices about that. So we did some work there too, and I'll talk about those 3 papers. Adam graduated, I'm happy to say, and is working at Johns Hopkins laboratory in the Baltimore area. Okay, so I went back and I found some spring primary headlines. These are a little hyperbolic at times, but I wanted to share these with some of you because this really motivated some of our research. Election officials have to make really hard decisions about resource allocation, and they are not often trained in operations research. They don't intentionally make bad decisions. They just need decision support tools to help. Let's start with this one here. A Wisconsin primary recap, voters forced to choose between their health and their civic duty. Okay, this is in the New York Times, so it made national news. And this alludes to the polling consolidation decisions I mentioned earlier in Milwaukee. It also, it also mentions that we are the first major election during the stay-at-home order. The other 2 have to do with polling consolidation decisions. I wanted my vote to be counted. South Carolina, a peek at COVID-19's impact on elections. And it mentions the equity issues right in the byline there, that the burden fell primarily on voters of color. And then there was also polling consolidations, I think the following week or very recently thereafter in Georgia, that were even worse. It was very chaotic, long lines, voting machine issues plagued Georgia primaries. So we actually have reliability issues here as well as queuing issues. And none of these problems were the result of any anybody trying to really throw a wrench in the operation of elections. It was just election workers trying to respond to the changing conditions without really having the proper tools. All right, so elections in the US are run at the local level, sometimes more at the state level, but they can be different. 2 states, Washington and Oregon, have, all of the elections are by mail, but the rest of the states usually have a mix. The models are pretty generalizable. It's just all the details might change according to the jurisdiction. So we do pick representative case studies for our analysis. But in general, sometimes you can decide to vote in person or by mail. So if you decide to vote in person, you might go there, check in, mark a ballot, and submit your ballot. And the picture at the top might show that voters are sorted aside and they have an assigned polling location. And you can also vote absentee. So in some states like Wisconsin, you can vote in person absentee. That's not illustrated here. We just show the mail ballot, which is the most common way to vote absentee. So you request a ballot, you receive that ballot in the mail, you can mark up the ballot, and then the voter has a choice to put the ballot in the mail or to use a dropbox in some areas. And I have a picture of the dropbox I used to cast a ballot in 2020. It's right outside the library. It's right next to the post office box. And you can't read this print on this little sign there, but it says, don't put your library materials in the Dropbox. Use the slot up there at the library machine. So it's kind of an ad hoc solution. But it did replace this tiny, tiny little box that you could put your utility bills in. It just wasn't big enough to hold the elections. But election officials did respond and build these boxes. And many of them have to undergo surveillance, and they're like tamper-proof, and they meet some specifications. Okay, but that will be the last problem I talk about. Just for a show of hands, who cast their ballot by a Dropbox? One. Okay.
I think the better question is how many people cast votes.
Oh, that's true. It's a very international crowd. Okay. All right, so I want to kind of mention some of the research that's been done. I'm also asked about gerrymandering. Gerrymandering is really interesting and a fascinating and challenging discrete optimization problem that really looks at issues of representation. And I don't look at the who votes for what in my research. We just focus on getting people to vote and making sure that they don't have to wait and that we meet other election criteria, regardless of what, how people vote. But I'm familiar with that research as well, but it's omitted here for a reason. There's a number of queuing studies where people collected real data and estimated the queuing aspects of voting, because what really captures the attention is long voting lines in person. And that's a big problem. There's also a big literature on allocating voting machines, the electronic voting machines. So Mir Yang, who's a professor at the University of St. Thomas here in Minneapolis, is an expert, and he's written many of those papers and looking at different methods for allocating those machines. And we use that information in one of our papers. And then I do a lot of cybersecurity research. So I was very interested in the attack trees and the voting risks. And I have another student working on security related issues, which is also sort of interesting. All of this research focuses on normal, mostly in-person elections. So some of the voting system risk incorporates risks to voting through mail. But we really wanted to look at some of the new issues that emerged since 2020, specifically responding to the disruptions and also design issues. Okay, so this is kind of an overview of the 3 papers that I'll talk about. 2 will be about voting in person. The first paper we tried to do it quickly initially. The initial analysis was very quick, so we could get it to election officials prior to the general election. And we used a discrete event simulation that's based on some of the previous studies to simulate what could happen in the election. Also, we studied the impact of using big sports arenas, which was proposed to help people vote. And then I'll talk about the polling location consolidation problem, which uses integer programming. We also simulate the results there, but the main contribution is the integer programming model and analysis. And then the third paper I'll talk about is the ballot ballot Dropbox location problem. Kind of focuses on this aspect of voting. Right, so eventually we'll sort of cover all the spots, but this is what the roadmap for today's talk. Okay, so I'll start with our first paper on designing pandemic resilient voting systems. So we were able to make so much progress so quickly. Oh, here we go. Because there exists some discrete event simulation of elections and also some data that we could use from pre-pandemic elections to at least aid us in our initial analysis of our model. From the very beginning, we used real data from Milwaukee, Wisconsin, because of the voting issues that were there and that got national attention. And we were able to actually to get news footage. We couldn't do any like research in the field. So we had to like watch news footage and like estimate certain parameters, but sometimes use an educated guess. We have pretty good data for this. We do not have electronic voting machines. We use the optical scanner. I always want to call it the optimal scanner, but the optical scanner. The process is that the voter arrives and checks in. That's usually the bottleneck. They've got the big voting booths. They check in. What was new was a lot of the PPE here. Okay, so I don't have pictures of it. I have pictures elsewhere. The poll workers would have masks, face shields, gloves. There'd be some hand sanitizer there on the desk. Voters were asked to also have proper covering and also to bring their own pen. So this is the bottleneck, and it got a little bit slower. We wanted to take that into account. We have data from prior elections without the PPE, of course. Then there's like a voting booth queue. Usually this is pretty short, but in 2020, maybe some jurisdictions couldn't accommodate all the voting booths while also maintaining social distancing. So we took that into account in the analysis. And then there's another queue over here when a voter submits their ballot into the optical scanner. Okay, so the vote gets count and then you drop off the ballot. So there's a paper backup, which is really secure and I recommend. And then you didn't really get a sticker that year typically because that would have been too much contact, which is a bummer because the stickers are great. And then the voters leave. All right, so we used Milwaukee as our guide, but a lot of the insights are more general. And so we looked at what the metrics were, how they would change for various situations. We looked at the role of early voting. We looked at the role of a higher turnout. So 2016 was a little bit of a lower turnout, but we had other previous elections with a higher turnout. And it ended up having pretty high early voting and also one of the highest levels of turnout in the last 50 years. It was like just edged out by the 2004 election. Okay, so in our discrete event simulation, we outlined the process that I kind of stepped through in the last slide. There are some capacity issues. There was possibly like a long queue that could form outside that could look really, really long if people are waiting 6 feet apart as opposed to 2 feet apart. We also looked at the impact of like having a priority queue where voters who self-identified as high risk could just go to the front of the line. Okay, so then the voters would check in and we kind of snake around here. If a voting booth is available, the voter would mark the ballot. There might also be like sanitizing steps that we added in here that might slow that down if there's a queue. The voting booths themselves could be sanitized as well as the optical scanner, except there's a lot less touching on the optical scanner. Okay, and then parts of this are inside the voting location. We tried to measure that time as a proxy for exposure to virus, for example, and we measured that in the simulation outputs. And we tracked, there's a lot of insights from the paper, but I want to talk about the other 2 papers as well, so I'm just going to mention a few. One is we looked at a lot of different scenarios. I'll mention 2 of the scenarios here. One that was really of interest was the impact of PPE versus like a regular election when there wasn't PPE. And we look at a few of these are on the left. Oops, there we go. The wait time is something I'm going to be talking about a lot today. So we want the wait time to be under 30 minutes. And if you look at that graph, you can notice that there's 2 distributions, the blue and the red one. There's very little overlap. And the red one, which has a longer wait, and that's the distribution with PPE. Just adding these few seconds to the check-in time really led to very long wait times in a high turnout election for like typical levels of early voting. So a survey said that 54% of Wisconsinites were going to vote early. In actuality, 58% did. An even higher number did in Milwaukee, probably due to the spring primary fiasco. But this was concerning to us that presence of PPE could make a big difference. I would not have guessed that before doing the analysis. We also looked at the impact of the poll worker shortage, and that was pretty enormous. And this is on top of the issues of PPE over here. These distributions don't overlap at all, and like losing a check-in booth would mean very long waits. So this was about, up to about an hour and a half at this polling location, but that was even longer under some of the scenarios we considered, especially if not as many people voted early. So we looked at a couple other situations, different levels of turnout, different levels of early voting, and the impact of voting at the Fiserv Forum where the Milwaukee Bucks play. And basically that was risky because if you have 182 polling locations, filtering a few of their voters into one mega location, the lines could get really bad. There would be a tipping point in there. And we found it was much better to have voters vote at their regular polling locations and just make sure that there's an adequate number of poll workers. Now, the solution, the mitigation to poll worker shortages is for the governor to call in the National Guard, to have the National Guard work as poll workers. That requires a little bit of planning ahead of time. And luckily, all of the poll worker shortages were filled by the time of the election. All right, so I want to move into our more recent work, which I think is a little bit more interesting. I kind of already told you a spoiler that the consolidating polling locations problem turned out to be kind of interesting when we studied it. And queuing is really important to this problem. And this problem came about because we started presenting our previous work and we got into conversations with Duncan Buell, who's a co-author on the paper, who's a emeritus computer science professor who's done a lot of work in election resilience and has done expert testimony. And we started talking about the challenge with consolidating polling locations. He was at the University of South Carolina and mentioned their specific problem and was able to share some data from Richland County, South Carolina, that we used for our case study. And usually consolidating polling locations is, kind of like a one-off decision, but there were some mass changes in polling locations in 2020. And I'll mention those a little bit more in a minute. But as a reminder, this is going to be all in-person voting. This is really where people go to that polling location is for in-person voting. And that will be the focus here as well. I'll talk about why we might want to consolidate polling locations in a second. But first, I have this nice picture here showing a region with 5 population districts assigned to 3 polling locations. And then there are some server resources. These are voting machines that would be allocated to those regions or those polling locations based on maybe some of the decisions that were made. So that's where some of the queuing dynamics come into account. What happens sometimes is that, let's say a polling location has to close. So this polling location 1 over here has to close. Then this involves some decisions. Should we move that to a new polling location? Should we consolidate? So here they're consolidated down to 2 polling locations. And these voters up in the green area are reallocated. And that might affect the server resource decisions as well. This actually happens all the time. It just happened a lot in 2020. There's some examples. Sometimes construction means that you can't really use a polling location. That really affects the accessible voting, like curbside voting that happens. Schools are less commonly used because of mass shootings. They've become less desirable for holding elections. Sometimes there's budgetary reasons and they just have to consolidate and use fewer locations. And sometimes, like in my home state of Illinois, they have historically voted in assisted living facilities. And that was kind of a bad idea in 2020. So there were a lot of different changes. And actually, that's the last time I voted in person on election day was in 2004 in an assisted living facility when I was living in Illinois. And I've requested an absentee ballot ever since because I really hate waiting in line. And I did wait more than 30 minutes that year. But this is a common problem that I was a little less familiar with before doing the research. That's really important. Other people have studied this, but not many. And there's only 4 papers that we could find. They all study non-US based systems, so some of the specifics are different. They also did not address all of the issues that we felt were salient to elections. They didn't really focus on this optimal consolidation. So we were interested in selecting polling locations, which can include consolidation. Also including capacitated facilities. I'll talk about the need for considering that in a moment when I introduce the model. Of course, resource allocation. So I alluded to having to allocate voting machines. That's what I mean. Contiguous districts. It's what people want, but it's also sometimes the law. And we also really wanted to consider queuing because there's a few metrics that are used there's many metrics to evaluate voting systems, but there's a few that to evaluate like in-person voting systems in real time. And the wait time is really, really important. And so our paper includes all of those issues and we're the only ones to do that. Yes.
So the consolidation happens in advance, it's not on the day of the.
Correct.
Okay.
There's a lot of laws involving when consolidation occurs. The question was, does the consolidation occur in advance? Yes. Every state or every jurisdiction will have a law telling you how many days in advance they have to do it. And you don't want to do it because people know where to vote and it's this old place. So there's a big downside to changing it.
And then they have to be informed where to go.
Yes.
And how do you assign the new polling locations for individuals based on a distance?
There's also laws about how to choose a new location. They're not real prescriptive though. So for example, I'm familiar with the laws in South Carolina. There's a law that's something like you can't travel an average of like more than 5 miles. Okay, but that might be from the center of your population district to the polling location. So there's like some constraints. The constraints here, some of them are really, really hard constraints. You can't violate them or there'll be a lawsuit. Some of the constraints are soft, but people will be really upset if you don't follow them. And that's mostly the Dropbox location problem. But these are good questions because there's a lot of legal requirements that are really strict. And we can work with those. And I'll allude to a few more as I talk. Okay, so we have a lot of sets and parameters. I'm going to introduce them, but don't worry if you don't keep up with them, it's fine. You could just read the paper later on. I'll explain most things with a picture. Okay, so we have a set of population districts, I. We have a set of polling locations, J. And then let's say J of I is the standard polling location. So everybody has a previous place where they voted. Some of them might be closed, so some of them might not be feasible in the new solution. So I know that there's construction and we can't use that location. But that's something to come. P sub I is the population for the population district. They're not quite even, and they can be quite uneven in some areas. And our main decision variables are these X variables, which is Xij is 1 if polling population district I is assigned to vote at polling location J. So this is like your classic assignment problem, but it's got a lot of other additions to it. And then we also have the resource allocation decisions. So the YJM is 1 if at least M voting booths, our servers, are allocated to polling location J. Of course, polling location J has to be used to get any voting machines allocated to it. Okay, so there's 4 key dynamics, one of which is the objective function. And there's a question in the back.
So I guess this is specifically for consolidation then, not say if I wanted to add another location, how would I do it? Because we're assuming that each population district has a single location where they're going to end up voting. So we couldn't further partition a population district.
You can't further partition. Right, but you can introduce like a new location that people haven't voted before. That would just be a J.
Right.
That's a good question. Okay, the first key dynamic is the polling location capacity. And this also is like the result of a bunch of laws. So you have to take this part seriously. And there are these limitations that we have outside of the servers that we allocate, that you need like enough space to hold the election. Mostly it's parking spots and the ability to have curbside voting and enough space for the accessible voting. And there are ways that election officials allocate this. We ended up looking at Google Maps and we're counting parking spots. We got down to that level of detail in our case study. So you can't consolidate a bunch of locations to this tiny little polling location that can't support the number of voters. The other limitation was with the voting machines. Okay. There's a certain maximum number of voting machines that can be accommodated in a location. Many polling locations are pretty small. And we estimated by the size of the building and tried to get some historic data based on who was assigned there in the past. And this also leads to the queuing of voters. That's a different key dynamic though. Mm-hmm.
So can you assign a population of people?
No, but I wish you could think about that. The question was, can we assign a population to multiple polling locations? And that's tricky. That's kind of impossible if you have like physical books. And yeah, but that's not how we do it in the US. The closest we got was like maybe we kind of flirted with having people also be able to vote like at professional sports arenas in addition to the local area. But I think that's an exciting potential area of future research, but not one that we considered. Okay, second key dynamic was wait time. And so the Presidential Commission on Election Administration said that no citizen should have to wait more than 30 minutes to cast a vote. This is great. We've got this directive here. So we model this as an MMCQ. Okay, so the service times being exponential is maybe a slightly dubious assumption, but there's a reason for using this type of model. Of course, queuing models are typically very nonlinear. But we really wanted to capture the queuing as endogenous to the model, not something that's like modeled with just the inputs. And it's a function of the assignment decisions and then the servers assigned to a location. So we need to know with the population that could show up to vote and then the number of servers. Okay, so we model this as a chance constraint. Okay, so we want like 95% of voters to be able to vote. Or the probability that the wait time is greater than 30 minutes to be less than 95%. Okay. So we can model this using, probability models. Okay, it's very nonlinear. And we found a nice paper where you could actually model this using a linear constraint. So this made me very happy. One thing, if you notice, it's actually a series of linear constraints, is that you have these lambda, alpha, m parameters, and these are parameters that would have to be pre-computed in advance to help model this. Okay, so we can address this in our linear model. And then the third is contiguity. So this is an example with 5 polling locations and some different population districts. The red ones are not contiguous. And this is bad. This is what causes people to like mistrust an election. So like these resource allocations decisions really help people trust in elections or not. Because people will wonder like, oh, why did Jay have to travel so far to vote? That seems really unfair. It's like somebody's trying to rig this election. But in reality, sometimes it's illegal. Okay, so it's also politically not viable, as I just mentioned, and quite often illegal. So we want to not do illegal things in the model. So we're going to add that as a constraint, and that will help us follow the law. And we want contiguous solutions. So to use this, we use a contiguity graph. This is one based on the United States, not the jurisdiction in South Carolina, but it illustrates that we have an edge between population districts that share a border. So we have an edge between states that share a border in this picture. And we use an IJ separator to add a series of constraints to the model to enforce contiguity. So this is summarizing a lengthier part in the paper, but this gives us contiguity. The last dynamic I want to mention is the objective function value. And this took a little while to represent because at first blush, we just want to minimize like the total distance that a voter would travel to vote. But this could actually lead to bad choices. And so we worked a lot on this. So we know from many studies that a longer distance that a voter must travel leads to lower turnouts. Okay. Turnouts, we want a high turnout. This is the point of all of this. So we modeled the distance between each population district and each polling location. Okay, we have a baseline distance in existence based on where they voted last, whether or not that's open. And there might be a new place that they're assigned that would have a new distance. And really, we really focus on the additional distance that they would travel. And the reason for this is because there are often polling locations that are closer to those voters. And we didn't want to encourage them all these extra reassignments that would happen based on this, which easily became a problem. So we just focus on minimizing the additional population weighted distance that would occur as a result of the consolidation. And this is mainly because, like, in urban areas, there's a lot of polling locations that are close to each other, and it we needed it to work out with the data, and this worked quite nicely.
What is the?
Oh, that's a population in each. Yeah. So I believe in the data that we have, there are very unequal populations in the model.
Actually, you're penalizing the extra distance. But,
Yes.
Why, if suppose the polling location is even closer than the previous polling location that you cut off the lane?
Yes, yeah, because we don't want to move around voters unnecessarily, because many just won't vote and they'll show up in the wrong polling location. We also could have like locations like swap polling locations, and so I show up and it's open, and then I wait in line and oh, I showed up in the wrong spot. So we needed to be able to avoid a number of situations like that. That's a good question. And somebody else had a question, maybe? Okay, same question. Yeah.
So in principle, you could build the objective function, something like a benefit if the polling location stays the same as the reference location. Yeah, like you're sort of using this to implicitly encode that there's a cost to switching.
Yes.
You
Yes,
could
exactly.
Explicitly encode it.
Yes. But as we'll see, which might be in the next, oh yeah. So, okay, the models, this is intentionally small, so you don't read it all, but if the standard assignment is feasible, then it's optimal. Okay, so that was good. This is a property that we wanted to have of the model. And it also is something that helps election officials trust the work that we're doing. Of course, the model is NP hard. It's also NP complete to demonstrate that a feasible solution exists. And it's mostly because of like our non-server resource constraints, which at this point, we just kind of sat back and we're like, wow, this is really interesting that we ask election officials to solve this problem. And it's really hard to solve. And they have a hard job to do. And I really appreciate election officials a lot more after formulating this model.
So what would be the standard assignment?
That would be like wherever your current polling location is.
But then the problem is when you remove some polling location.
Yes. Then it would no longer be feasible. In that
Okay.
case, that's the only time it wouldn't be feasible, is if some of those standard polling locations are no longer open in the next location.
What is the optimality of the standard assignment?
The optimality, well, it would be optimal the whole problem. So if the old solution is feasible, the next solution, meaning that all of those polling locations are still open,
Oh,
then
okay.
it becomes optimal. And also that you have like enough, yeah, like the parking lots didn't shrink or something. Okay, so we use Richland County, South Carolina as a test bed for this. And has 265,000 registered voters, 149 voting precincts that are assigned to 129 polling locations. This is a map of the area. They have 5 backup polling locations, which is interesting. So election officials they prepare for all sorts of contingencies, and that some of them they pre-file ahead of time, which is what we hope they do with solutions to models like this. In 2016, they had a 61% voter turnout, which 42% was in person on election day. And we assumed the server resources were 981 voting machines, which would accommodate what they had in the previous election. And we want 95% of voters to wait less than 30 minutes. And to compute distances, we used big maps and sampled a lot of distances within each polling, within each precinct. We studied a lot of different aspects of in the solutions. I won't have time to talk about all of them. I will talk about a supply disruption, which is what happens when you don't have as many voting machines as you hoped for. So that could occur because maybe a vulnerability is discovered in the software and you can't use that model anymore. And so maybe you're just out like 20% of your voting machines. So in our base case with 981 polling locations, you can see all of the optimal assignments. So like little dot is the polling location that's each district is assigned to, and the line takes you from the center of that polling location to the center of the precinct to the polling location. Okay, so that's like a good solution. I think a couple of the locations couldn't be used, so there's just a couple of swaps. When we decrease to 810 voting machines, that's a pretty big decrease. You can see that there are some consolidations that occur and that multiple population groups will be assigned to a single polling location. But we can still satisfy the problem, and we can still assume sure that people won't be waiting longer than 30 minutes, which is amazing to me. Math is beautiful. Optimization is wonderful. And we can further consolidate by having even fewer voting machines available. So this is just like 15, but this is where there's a tipping point. It becomes very painful and difficult to make these decisions. We see some mass consolidations start to occur. Okay, so we can manage a pretty big disruption if we use optimization. Like optimization is great. We also were interested in what happens in some of our cases, like why there are so many mass consolidation locations. And we looked at these locations, and some of these were like these backup locations that were very big locations, like a high school gymnasium, that happened to be located by the interstate or highway. So when we computed driving times and some other metrics of distance, that they would be very accessible to many voters. And we said, well, those are handy, but what if you don't have those available? So then we took those out, just those 5 locations, we took them out of the analysis. And if they're not allowed, we're measuring total added transit time on the y-axis. We have that to be low. With them, we have this black line. So you can see that we don't add any extra transit time as we decrease our number of voting machines, and then at some point it increases. But this red line, where we don't have these big polling locations, it can get much worse, much quicker. But still, in both cases, we're able to consolidate and to deal with many voting machines not being available. Okay, so this is something to think about. I don't know if this holds totally in general, but it seems like mathematically this is probably a pretty good bet and something that maybe election officials should work on identifying ahead of time. Okay, so if you're really interested in like a big table of results where we reduce the number of servers, which is over here in the first column that goes down. One thing to keep an eye on is the second column, which is the total amount of transit time. It's not 0 because we had to like make some of the locations unavailable, but it's about 1,200, which is not that much compared to the total population. And actually, we can decrease from 981 voting machines to about 830. And we have to reassign just 5 precincts, impacting 13% of the population, just over 5% of the population. We can handle that kind of disruption. So we just have to be smart about it. These are not obvious decisions, and they would be hard to identify without optimization. But after that, it becomes harder. So we can go down to 795 machines, and you can see that the precincts reassigned increase, but we're not really adding any distance, right? We're definitely being disrupting more voters, but not making them on average travel far further, okay, which is also really interesting. And then beyond that, there's a lot of trade-offs. Okay, so this is like the positive side. With great planning, we can avoid many of the worst disruptions.
So this is under the solution of the optimization problem.
Yep.
So what is the optimization problem considering the objective function considering the rate cost? You have a proxy for that, but just
Yes. Yes. We did some simulations, so this might, yep, as well. We simulated the results.
so coming back to the objective question, so objective function. The objective function, the penalty is the difference in the distance.
Yes.
It's a linear difference. Shouldn't you be using the
Oh,
so quadratic part of the reason is because then looking at the micro foundations for that cost, if each individual's cost distance from the polling location to the thing at the square of that term, then moving a polling location to from one point to another, the aggregate quadratic cost of overall individuals just changes by the square of the distance, extra distance. The distance in the two
Yes.
locations.
yeah, that's a good question. And that would also just be a constant in the model.
Yeah.
But because we have this law that saying you can't really assign people to really far distances anyway, because that would be illegal, we didn't consider that. But that would be a good safeguard against cases where maybe there's not a law like that. Yeah. Good question. All right, so I know I'm running short on time. I want to mention dropboxes because they're so exciting. Again, this is just helping people vote by mail or vote by mail by using a Dropbox that in the voter's mind might go directly to their election officials without having to go and travel through the mail. And I was so excited on election day, about a month ago, that the state of Michigan passed a new law about Dropboxes and that they have to use them. And the requirements are one Dropbox for every 15,000 registered voters, at least one for every municipality. And I thought the most interesting part of the bill was that the Dropboxes would have to be distributed in an equitable way. And I have written a paper on equity and location decisions. This is not straightforward and there's not a single model for that, but it does reflect the fact that people want these to be equitable. And I agree. I think this is a great goal. But I think there's a lot of different laws regarding Dropboxes. I can answer questions about those afterwards, but a lot is being considered thus far. Luckily, we can use integer programming to help us make some of these decisions. Okay, so you might be wondering, like, do Dropbox locations really matter? And I will say, yes, they do. In fact, because you don't have to vote. In some countries like Belgium, I learned today, but residents have to vote. It's required by law. But in the US, we don't have to vote. It's a choice. And we actually want to lower the cost of voting so more voters choose to vote. And there's actually been some research in Dropboxes that show that people are more likely to vote if they have access to a Dropbox. And they're more likely to trust in the system because they voted. And they like Dropboxes, actually. And voters use Dropboxes primarily for three reasons. One is because they might be close. They might distrust the postal service. They might anticipate mail delays, which I think was a reality in 2020. And especially voters that live in like apartment complexes where their mail is just sort of out there and people can, they might just feel like their neighbors might have access to their ballot. They use the mail. And so that's a big piece of it. We actually read some like survey results for why people might want to use a Dropbox. Okay, so the idea here is that if we can improve the access to the Dropboxes, we can encourage more voters to vote. And we're not going to make radical changes, but it's these small incremental changes. And the fact that it became a law in Michigan reflects the fact that I think a lot of people actually do find Dropboxes convenient. So we are going to focus on the costs and risks associated with Dropboxes, mostly by their location. Okay, so we're going to return to our case study in Milwaukee. We're not allowed to use Dropboxes in Wisconsin. Unfortunately, those our Supreme Court ruled that we can't use them, but we can pass a new law if we want to that explicitly allows us to use Dropbox locations. But at the time, we were doing this research before the Wisconsin Supreme Court decision. We went back to Milwaukee since Dropboxes were so popular in 2020. We have a potential Dropbox location, so you don't want to locate them everywhere. We have demographics and voter data. And then we want to produce different maps that election officials can use. Giving them some choices is good. So you don't necessarily want a single solution. We want a series of solutions. And then we kind of came back to this idea of a covering problem. We want to minimize the cost of adding drop boxes so that we cover voters, maybe at least once by a drop box. And as we sort of dug into this, we didn't find a lot of hard constraints, but we found a lot of constraints that were given to us by people who wanted drop boxes to work in a certain way. And I think they're reasonable, and I think they're coming into reality in terms of being added to laws. Okay. So right here, we have the basic location set covering problem, a set of voter locations, a set of potential Dropbox locations. We have some of these locations that might cover a voter, and maybe this is by distance that we've determined. And then we also have the cost of a Dropbox, and they're not all constant. They can be. Some might need surveillance in certain areas, et cetera, based on where they're located. But we do have a cost of Dropboxes, and I mean, we wouldn't want to put them on every street corner. These costs are important. And so YJ is 1 if a Dropbox is located at J. We noted that there was a pretty significant operational cost, and that daily, typically, up until an election, a bipartisan team of election officials has to collect all the ballots. So they have to do a tour of all the ballots. So this is exciting. This is something that we knew about, but it's not a traveling salesman problem because we're not going to be visiting all of the potential Dropbox locations, just the ones that have a Dropbox located at it. So that was an interesting part of the problem. And we wanted to look at this as a big part of the cost. So this adds some new parts to our model, parts in red here. They have travel costs, edges in the sets of the graph, and then these XIJ variables reflect the tour. Okay. And we also wanted to look at equity, and this is multiple voting pathways. So now voters can vote all sorts of different ways. They can vote in person on election day. They can place their ballots in the mailbox, or they can use the Dropbox. And here we use discrete choice theory with the idea that, here's my function. It's based on the accessibility, which is not like kind of a disability accessibility. It's just closeness to the voter. So we look at a voting location, J. We look at also their propensity not to vote, which we have historically for different subpopulations in a region. And we look at the access to the non-Dropbox literature. So some neighborhoods, they might be pretty close to their local polling location. Maybe it's just around the corner. And some maybe have to travel further, and that will affect their access to the non-Dropbox voting infrastructure. And we try to measure this function using historic voting data. And we want this value to be closer to 1, which implies better access. And we turn this function into a constraint, and we try to get all the locations above a certain level. So this allows us to potentially locate the Dropboxes, not just in a way that covers all voters, but that might be located in some areas where there's been lower historic vote, or maybe it's a little bit further to the polling location. And this helps us be more equitable about locating the Dropboxes. And this becomes a constraint in the model. And R is a minimal access function. Okay, so I will just say that there are some Dropbox risks, but I won't get into this in the interest of time, but most of the way we address this is sort of baked into the model. And we can also consider backup coverage if we want. Okay, so we have a Dropbox problem. It is NP hard. We've got this facility location problem. And we did recognize that in some areas you can reduce some of the constraints. And this usually has to do with the corners of a population district. So it makes it a little bit easier to solve the problem. I will mostly skip our solution methods. We do use a heuristic that optimally solves a relaxed version of the problem, which is pretty easy. and then swaps to come up with a series of non-dominated solutions that are actually quite good. And this is helpful for election officials. And we like having a lot of solutions. I'll show you pictures of those in just a second. In our case study, we consider the county of Milwaukee. We consider a bunch of potential locations, which is like a lot of government buildings, plus we use CVS and Walgreens, pharmacies, you could use schools or something. And we looked at all sorts of like demographic data to estimate the costs. And then we looked at the cost of the dropboxes, which actually cost $6,000 to $10,000. We were able to compare the model solutions to the actual dropboxes used in 2020. We have a lot of criteria here. Only a couple of them are included in the model. Our solution models are in this rightmost column, and they're better in all the criteria we considered except for two, is slightly worse. So we're able to identify good, meaningful solutions. Okay, so what do our solutions look like? Well, here's three solutions that we have in our model with more Dropboxes as you go to the right. And you can see the solution tour. It's as the crow flies, but we actually computed actual road distances in here. And this, I would not, these are pretty non-obvious to come up with without using an optimization-based approach. You can see that the tours are actually fairly compact. They can really respect the election officials' times, because they have a lot to do leading up to the election, and having a shorter tour is a good thing. All right, so with this, I want to kind of wrap up my talk and say, I hope these are not my last three papers on election resilience. This has been a lot of fun to work on. There's a lot of insights and policy insights that have come out of these models. I really believe in the importance of taking research that affects the public to the public. So one way that I've done this is I published 3 op-eds, all on the Hill actually, about the research. And the most recent one was about the science of dropboxes. And that one generated a little controversy, but I'm glad people read the article. So with that, I want to thank you for your attention. Mm-hmm.
So, you're get like lowering the cost. Have you found that this is used as sort of gerrymandering, like lowering the cost in places that?
Oh yeah, I do worry about people misusing the science and like doing the opposite. And then really what, well, yes, I do worry about that. But I have a stack of newspaper articles where I don't think that was the case. Election officials just made poor choices, and it probably did affect turnout, and it did cause, well, not trust in the system. I think there's just a lack of real tools. Also, there's this MIT Election Center that they actually have this online tool to help election officials estimate the number of check-in booths and voting machines they need with just simple points of data. And that's one thing that I'd like to build is a website to help election officials, because that tool has really helped a lot of election officials avoid problems of resource allocation. So in general, I think that the good outweighs the risks, but I do take the risks seriously as a security researcher, always thinking about people using the rules and the models to do something that you don't want them to do. That's a really important question. Okay. I didn't hear the whole one kind of what we're actually. Oh yeah. Our equity concept was mostly in the discrete choice model. Without that the discrete choice model, without those series of constraints, if the Dropbox would be located to everybody sort of equally, but we're trying to take and say, well, some people are going to vote anyway. So in the areas where there's less voting, that's where we want to sort of encourage more Dropboxes located. You could also argue that like coverage models are a model of equity. And some, yeah, I I actually wrote a paper on location and equity, so that could potentially be a long. Yeah.
Between your Dropbox and other like. Dropbox.
Yes, I'm working with somebody who studies networking about that. That could be a source of actually extra resilience if you plan, because, you know, like, oh, well, we were co-workers over here because there's all the Dropboxes. So you can, that can actually be more inclusive. But having, your question about equity is a good one, because the recent laws point to equity maybe being measured a different way. But really, you're competing with not voting. That's like the biggest competition. We want people to vote either in person or absentee.
Asked to make the checkings of different options here. How do you?
Yes, I forgot we had that. So I think in the paper, I picked the details. We use some data for that. I'm satisfied with how we did that, but I'm not so confident about the predictiveness models. That's what I'm kind of curious about the latest science, maybe some of which haven't been published yet, about how Dropbox is like. That would be nice. And some natural experiments. There's a lot of preliminary data out there in the archive, whatnot, but I'd like it to be peer reviewed.
So unrelated note, the best not to vote. That explains what is the choice options.
Yes, it probably would be. Some votes, elections just attract more voters than others, so that it's a little bit. Yeah, not yet. I have to also review the data because. Yeah, there's a lot of disparities between like students in our data, so some have a high propensity not to vote election. Yeah, just sort of curious about how much we move the needle. To me, that's the question.
So for the second, the polling booth location, so is it possible to incorporate like have the objective that it's just the amount of time a typical voter have to spend through the whole process, where like now also include the traveling time, so it's the distance is becoming sure plus you already have a green model, so that's something that you have to look at.
So, yeah.
Just minimizing that might even as a theoretical exercise, like probably more possible changes, just like what is more possible.
Right.
Such a time.
In that case, to reduce the problem with the optimal network coverage problem. Or say sunset placement.
Yes, possibly. Develop some more.
And there's a lot of new development in that area, especially coverage problems. Demonstrating, actually creating algorithms, because once you have demonstrated submodularity, or even in the absence of submodularity.
Oh, yeah.
New 3D techniques that actually work pretty well. Okay. In fact, a lot of new developers in machine learning.
Okay.
Optimization.
Well, maybe you could point me
Yeah,
to some of those. I'm familiar with some of the papers. Something new, I'd like to read it.
Okay, so we have a reception in the lounge, so please join us and let's thank Professor Albert once more.
To stop recording.